There's a star out there that breaks the rules. Stephenson 2-18, the largest known star in the universe. So massive that if you placed it where our Sun is, it would swallow Mercury, then Venus, Earth, Mars, Jupiter, and keep going past Saturn. One star, bigger than our entire inner solar system. That's terrifying. It's 2,150 times wider than the Sun, 10 billion times its volume, shining with the power of 440,000 suns. And here's the shocking part: it shouldn't exist. According to our models, stars this large can't form. They're too unstable, too violent. Yet there it sits, 19,000 light-years away, defying physics. Let's explore the monster. Stephenson 2-18 hides in the constellation Scutum, about 19,000 light-years from Earth, deep in the disk of the Milky Way. American astronomer Charles Bruce Stephenson first spotted the region in the 1970s. He was conducting a deep infrared survey, looking for cool, massive stars buried in dust. He found an open cluster, Stephenson 2, one of the most massive star clusters in the galaxy, packed with 26 red supergiants, the largest known population in the Milky Way. Among them sat object number 18, later designated Stephenson 2-18, also called ST2-18 or RSGC 2-18. At first, astronomers weren't sure it belonged to the cluster. It sat too far from the core, moved slightly differently, burned unusually bright. Measurements came slowly. The star is heavily obscured by dust. Infrared observations only. Regular telescopes can't see it. Too much cosmic smoke in the way. By the early 2000s, multiple studies converged. Radius estimates climbed. 1,800 solar radii, then 2,000, then higher. A 2012 study using the Australia Telescope Compact Array and modeling software finally pinned it down. 2,150 times the radius of the Sun. The new record holder, dethroning UI Scuti and WOH G64. Diameter, 3 billion kilometers. If you could drive around its equator at highway speed, the trip would take 5,000 years. Light itself takes nearly 9 hours to circle it once. For comparison, light circles the Sun in 14.5 seconds. This isn't just big, it's incomprehensible. And here's the problem. Stephenson 2-18 exceeds the theoretical limit. Current stellar evolution models predict a maximum size of around 1,500 solar radii, the Hayashi limit. Beyond that, stars become gravitationally unstable. They can't hold themselves together. Yet, Stephenson 2-18 measures 2,150 solar radii, over 40% larger than theory allows. Why doesn't it fly apart? Massive stars form from collapsing gas clouds. Gravity pulls material inward. Fusion ignites in the core. Radiation pressure pushes outward. The two forces balance. For most of a star's life, this equilibrium holds. But red supergiants push the limits. They start as massive O-type or B-type main sequence stars, between 10 and 40 solar masses, burning hydrogen in their cores. Eventually, core hydrogen depletes. The core contracts, heats up. A shell of hydrogen around it ignites. The outer layers expand. Dramatically, the star swells from 10 solar radii to over 1,000, sometimes 2,000, all while the core shrinks and heats. This creates a bizarre structure, a tiny, dense core, a vast, diffuse envelope. The outer layers have densities millions of times lower than Earth's atmosphere. Convection dominates. Giant convective cells churn through the envelope, moving material up and down, taking months for local cycles, years for global oscillations. The star pulsates, expands and contracts rhythmically. This motion lifts material from deep layers toward the surface. At several stellar radii out, temperatures drop below 1,500 Kelvin. Dust forms, silicates, carbon compounds. These particles are opaque. Radiation pressure from the star's luminosity pushes on the dust, accelerates it outward. The dust drags gas with it, creating a wind. This is how red supergiants lose mass, through dusty, radiation-driven winds. But Stephenson 2-18 takes this to an extreme. Its luminosity is 440,000 times the Sun's. That's an enormous radiation field, pushing relentlessly on any dust that forms. The star sheds mass at a staggering rate. About the mass of Earth is being blown away that every 25 days. That's roughly 1.35 times 10 to the -5th solar masses per year, among the highest mass loss rates ever measured. All this mass loss creates a problem and an opportunity. The star loses gravitational binding. The outer layers become less tethered, allowing further expansion. This feedback loop might explain how Stephenson 2-18 grew beyond the theoretical limit. Extreme luminosity, extreme mass loss, extreme size. But it also means the star is unstable. It's tearing itself apart, slowly, steadily. To make this tangible, what if Stephenson 2-18 replaced our Sun? Start at the center. The Sun sits here now, 1.4 million kilometers across. Comfortable, stable, predictable. Replace it with Stephenson 2-18. The star's surface expands outward. Mercury orbits at 58 million kilometers. Gone. Swallowed instantly, deep inside the star's envelope. Venus is at 108 million kilometers. Consumed. The star's outer layers envelop it completely. Earth is at 150 million kilometers. The planet we're standing on, vaporized, inside a diffuse plasma, thousands of degrees hot. Mars is at 228 million kilometers. No escape. Engulfed. The asteroid belt is at 300 to 500 million kilometers. Obliterated. Every rock, every fragment. Jupiter, the giant, sitting at 778 million kilometers, 11 times Earth's diameter. It wouldn't matter. Still inside the star, melting, disintegrating. Saturn is at 1.4 billion kilometers. This is where it gets interesting. Saturn's orbit sits right at Stephenson 2-18's radius. The planet would orbit at the star's surface, or just beyond it, skimming the photosphere, superheated, atmosphere stripped away, rings vaporized. Uranus is at 2.9 billion kilometers. Safe, barely, outside the star's physical boundary, still bathed in unimaginable radiation. Neptune is at 4.5 billion kilometers. Far enough, but still scorched. Everything from Mercury to Saturn, gone. 7 planets, the asteroid belt, Jupiter's moons, all consumed by a single star. And remember, Stephenson 2-18 is losing mass, constantly. The stellar wind would blast to the outer planets with a stream of superheated plasma moving at tens of kilometers per second. Even if Uranus and Neptune survived physically, their atmospheres would erode, stripped by the wind, leaving bare rocky cores. This star doesn't just occupy space, it devours it. But here's the sudden turn. Red supergiants don't last long. Despite their enormous size, they burn through fuel rapidly. A star like the Sun will live 10 billion years. Stephenson 218, maybe a few million, possibly less. Stephenson 2-18 is already dying. Right now, it's fusing helium into carbon and oxygen in its core. When helium runs out, the core contracts again. Carbon fusion ignites, then neon, then oxygen, then silicon. Each stage burns faster than the last. Carbon fusion lasts hundreds of thousands of years. Neon fusion takes a year. Oxygen fusion takes months. Silicon fusion takes days. Eventually, the core produces iron. Fusion stops. Iron doesn't release energy when it fuses. It absorbs energy. The core becomes an inert ball of iron, supported only by electron degeneracy pressure, growing heavier as surrounding shells dump more iron onto it. When the iron core exceeds 1.4 solar masses, degeneracy pressure fails. The core collapses. In less than a second, it shrinks from thousands of kilometers across to 20 kilometers. A neutron star forms, or a black hole if the core is massive enough. The outer layers slam inward at 70,000 kilometers per second, then rebound off the incompressible core. The shock wave tears outward, ripping through the star. Supernova. The explosion will be visible from 19,000 light-years away. Peak brightness, magnitude -8, as bright as a crescent moon. Visible during the day. The blast will outshine the entire Milky Way core for weeks. But here's the chilling part. It might have already happened. Light from Stephenson 2-18 takes 19,000 years to reach us. We're seeing the star as it was 19,000 years ago, in the late Paleolithic, when humans were still hunter-gatherers. The star could have exploded 18,000 years ago, or 10,000, or yesterday. We wouldn't know. The light from the explosion hasn't reached us yet. Somewhere in space, a wave front of light and neutrinos might be racing toward Earth right now, carrying news of the star's death. Within the next few thousand years, that light will arrive. The night sky will gain a new star, brighter than anything except the moon. Or maybe it has millions of years left. We don't know. Red supergiant lifespans are poorly constrained. Either way, Stephenson 2-18 is doomed, living on borrowed time. The truth. Most stars never approach this size. Why? Let's find it out. Mass. You need an enormous progenitor. At least 10 solar masses on the main sequence, probably 20 to 30 for something like Stephenson 2-18. Stars that massive are rare. For every star above 10 solar masses, there are thousands of Sun-like stars, millions of red dwarfs. Massive stars always die young. A 30 solar mass star lives only 5 million years. No time for many generations. Most have already exploded. Then there's the mass loss problem. As stars evolve and expand, they shed mass. Winds carry material away. The more luminous the star, the stronger the wind. By the time a 30 solar mass star becomes a red supergiant, it might have lost 10 solar masses, maybe more. What remains determines how large it can grow. Lose too much mass, and you never reach the red supergiant phase. The star becomes a Wolf-Rayet star instead. Hot, compact, blue. Entirely different outcome. Stephenson 2-18 somehow retained enough mass to expand to an extreme size, while simultaneously losing mass at a record rate. A delicate balance. It also needs the right metallicity, elements heavier than helium. They form dust. Dust drives the wind. At very low metallicity, red supergiants can't form efficient winds. They might collapse before reaching extreme sizes. Stephenson 2-18 sits in the disk of the Milky Way, metal-rich, perfect conditions. And finally, luck. The star needs to avoid binary interactions. A close companion would strip mass, disrupt evolution, prevent the extreme expansion. Stephenson 2-18 appears isolated. No obvious companion, free to evolve undisturbed. All these factors align rarely. That's why extreme red supergiants are so uncommon. And here's the fact that breaks your brain. Stephenson 2-18's volume is 10 billion times the Sun's. You could fit 10 billion suns inside it. Literally. But here is the twist. Its mass is only 15 to 25 times the Sun's, maybe 30 at most. Do the math. 10 billion times the volume, 30 times the mass. That means it's 300 million times less dense than the Sun. The Sun's average density is 1.4 grams per cubic centimeter, slightly denser than water. Stephenson 2-18's average density, 0.000000005 grams per cubic centimeter, 5 billionths of a gram per cubic centimeter. That's 200 times less dense than Earth's atmosphere at sea level, 10,000 times less dense than air at the peak of Mount Everest. You could fly a spaceship through Stephenson 2-18's outer layers for thousands of kilometers and barely notice. It's more vacuum than a star, yet it glows, radiates energy, shines with the power of nearly 500,000 suns from something so diffuse that it's almost imperceptible. This is what happens at the edge of stellar physics. Matter so rarefied, it's barely matter anymore, held together by gravity alone, burning itself from the inside out. And soon, it will explode, scatter vast amounts of solar masses into space, seed the galaxy with carbon, oxygen, silicon, and iron, the building blocks of planets and life. Every atom heavier than helium in your body came from a star like this, a giant that lived briefly, burned brilliantly, then died violently. Stephenson 2-18 is that giant, living its final days. And somewhere in space, light from its death might already be traveling toward us. When it arrives, we'll witness the end of the largest star we know. A cosmic event billions of years in the making. Until then, it sits in the sky. Terrifying, impossible. Stephenson 2-18, over 2,000 times wider than the Sun, 10 billion times its volume, burning to die, unbelievably unstable, the largest star we have ever found, and proof that the universe pushes boundaries we thought were absolute. Want more cosmic extremes like this? Subscribe. Drop a comment below on what stellar record you want to explore next. The universe has monsters. We're only beginning to find them.